All right, so problem 1.30 in the book, chapter 1. The compound Cr, C2H3O2, and this is called chromium, and this is the acetate ion. Chromium acetate is the name of this compound. This is actually chromium 3 acetate, is used in the tanning of leather. How many atoms of each element are given in the formula? So how many chromiums are there? Well, this Cr has no subscripts by it, so there's just one chromium. This subscript, 3, refers to whatever's inside the parentheses that the subscript is outside of. So for chromium, there's just one chromium. There's one chromium. For carbon here, this carbon atom right here, this is a 2. There's 2 carbons in this parentheses, and there's 3 of these parentheses. So that means there's a total of 6 carbons. 6 carbons. Hydrogen here, H. There's 3 hydrogen inside the parentheses, and there's 3 again of those parentheses. Therefore, there's 9 hydrogens. I'll put that up here. Can you see those okay? All right. Oxygen. There's 2 oxygen inside the parentheses, 3 of those 2. So for oxygen, there are 6 oxygen. 6 oxygen. All right. So there's 1 chromium, 6 carbons, 9 hydrogens, and 6 oxygen. Very good. So now we'll go on to problem 132. It says Epsom salt. Epsom salt is a hydrate. Now, a hydrate is a chemical that wasn't completely dehydrated when it was made, and so it has some water molecules, and there's a number of water molecules per formula unit of whatever that chemical is. So Epsom salt is a hydrate of magnesium sulfate, and it gives us the formula. Mg, which is magnesium, SO4 is the sulfate, magnesium sulfate, and there's 7 H2Os. So this is the hydrate form of the compound. What is the formula of the substance that remains when Epsom salt is completely dehydrated? Dehydrated means water is removed. So if we were to remove the water, these water molecules here, then we would be left with the MgSO. So that would be our formula for the substance that remains when Epsom salt is completely removed. Alright, so now we'll go on to 134. A molecule of acetic acid formed when wine spoils and becomes sour is shown below. Write the chemical formula. We have an image like this, where we have a black ball binding to another black atom, and these are binding to 3 white atoms, and this is binding to, black bond, red atom, and this is binding to another red atom, which is binding to a white atom. Alright? Black is carbon, white is hydrogen, and red is oxygen. Okay? Alright, so the question is, what's the chemical formula for this compound? Well, the chemical formula, we have 2 carbons, C2, 3 hydrogens, H3, but there's another hydrogen there, H4, and 2 oxygens, O2, C2, H4, 1, 2, 3, 4, O2. Now this chemical formula would be fine, but sometimes the chemical formula is written slightly different so that we can remember or remind the person who's reading the formula that there are certain groups on this molecule. For example, you might see this chemical formula written like this. So let me rewrite this, C2H4O2. C2H4O2. Alright? So I rewrote the chemical formula up here. Some other ways that this chemical formula might be written would be C2 H3O OH. That would be emphasizing that this OH group, reminding the person that there's this OH group coming off of one of the carbons. Another way that this could be written, CH3, identifying this group, COOH. Alright? CH3, identifying this group, COOH, COOH, identifying that second group. All of these would be fine for chemical formulas for this specific compound. If you're unsure which one to choose, you go with the most simplified one. Until you become more comfortable understanding why these types of forms are used, you don't have to worry about those ones. Alright. So that is 1.34. Now we'll go on to 1.36. 1.36, write the chemical formula of the molecule illustrated below. And the molecule illustrated below is what's called a space filling model. And you see there's one blue, this isn't a blue ball, but blue, I only have black here. And then there's 3 white spheres connected to that blue sphere. Alright, these are white. Okay, so I'll color in the darker one, the blue one, and the rest of them are white. So blue is nitrogen, so there's 1 nitrogen, and there are 3 hydrogens. Alright, so what's the chemical formula for the molecule? It's NH3. NH3. Alright, that's 136. And 138 refers to problem 136. For the molecule in problem 136, which of the following structural formulas is correct? Well, here we see we have a nitrogen being bound to 3 different hydrogens. So if we were to draw what's called a Lewis structure, or a structural formula for this, we would want the nitrogen in the middle, and we would want it to have 3 hydrogens being bound to it like that. Alright? So which of the following structural formulas is correct? This one would be the correct one. Alright. On to 140. In 140, the question is how many atoms of each element are represented in the following formulas, and for each of them, name the elements present. For each, name the elements present. Alright, so the first compound is K2C2O4. Alright, this is our potassium, and this is the oxalate ion, C2O4. The C2O4 has a -2 charge, and that's why there's 2 potassium ions. Now, we'll do a quick review here on how we know the charge on the potassium ion. Okay, looking at the periodic table here, potassium is in our first row. It's an alkali metal. Potassium is in the first row, and if it loses an electron, it will have an electron configuration similar to that of the noble gases. Therefore, potassium is willing to lose an electron and become a positively charged ion, like this, plus. Now the potassium atom has become a potassium ion, right? And in this compound, the potassium atoms are ions. They have plus positive charges. There's 2 of them, correct? So this is a positively charged potassium ion in this compound, all right? And from that, because we see that there must be 2 Ks, potassium ions, then we know that the C2O4 polyatomic ion must be equivalent in charge to 2 plus 1. So that makes it a -2. Alright? And that's why one of these combined with 2 potassium ions. So this is potassium oxalate. And in this compound, potassium oxalate, there's 2 potassiums. This 2 refers to the carbons. There's 2 carbons. This subscript 4 refers to the oxygen. Therefore, there's 4 oxygen. That's part A. In part B, H2SO3, H2SO3. This is the hydrogen, and this is the, not the sulfate, SO4 is the sulfate, this is the sulfite polyatomic ion. We can again look at what the charge is on that sulfite by looking at the charge that would be on hydrogen. Hydrogen always has a +1, and we see that there are 2 of them. So this sulfite ion must have what kind of a charge? SO3 has to have a -2 charge, right? All right, so this is called sulfurous acid. Sulfurous acid. That's similar to our strong acid, H2SO4, called sulfuric, SO4. Sulfate goes to ic, ite goes to us, so this is sulfurous acid. And we see that there's 2 hydrogens. This 3 only refers to that oxygen, therefore there's 3 oxygens, 1 sulfur. 2 hydrogens, 1 sulfur, 3 oxygens. All right, that's H2SO3. The next one is C12H26. All right, C12 means there's 12 carbons in one long chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right? So I made a chain of 12 carbons. 26 hydrogens means that there's 1, 2, 3, hydrogen, hydrogen, hydrogen. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 26 hydrogens. Now, how did I know how many hydrogens were on each carbon? Well, let's draw that again. This time I'm not going to draw the carbons, the C's. I'm just going to draw a structure like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the same thing. 12 carbons in a row. Each one of these points right here represents a carbon. This is a simplified way of writing it, faster than writing carbons out, right? Each carbon has to have 4 bonds to it in these organic molecules. An organic molecule, hydrocarbon, where you just have carbon and hydrogen. This carbon right now is showing 1 bond to its neighboring carbon. So it needs to have, how many did we say? We said it needs to have 4 bonds to it. So it needs 3 additional bonds. And in organic molecules, when we're drawing organic molecules, if we don't draw anything else, then it's assumed that there are hydrogens enough that each carbon will have 4 bonds to it. So that means this part of the molecule, this carbon has to have 3 hydrogens. This one has to have 2, this one has to have 2, and so forth until each carbon has 4 bonds. All right, so I know each one of these has to have 2 because this carbon here, how many bonds does it have? 1, 2 to neighboring carbons, and then it has to have 2 more to hydrogen. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So that's 26 hydrogens. All right? So C12H26, how many carbons? 12. How many hydrogens? 26. What's the name of this molecule? Well, 12. To say, when you're naming organic molecules, we use the Latin prefixes and the Latin words for 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so forth, depending on how many carbons there are. And we're familiar with one of these names that we use all the time when we're talking about gasoline. Gasoline, one of the main components in gasoline is octane. You go on, read on the side of the gasoline pump, it tells you information about how much octane is in the gasoline. Octane sounds like octopus because 8 means there's 1, 2, 3, 4, 5, 6, 7, 8 carbons. So octane is an 8 carbon chain. And you can also know how many, I'll write down C8, this is octane. Also write down how many hydrogens there are. I know because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's 18 hydrogens, right? So this is octane, okay? So oct, again, referred to 8. Dec refers to 10, and 12 is dodec. So this is dodecane, and that's the name of this molecule here, dodecane. All right, we're on to the next one, C2H3O2. C2H3O2. So right off we can see there's 2 carbons, 3 hydrogens. Oh no, it's HC2H3 O2. All right? 2 carbons, 3 hydrogens, 2 oxygens, but then there's one more hydrogen. So there's a total of 4 hydrogens. 2 carbons, 4 hydrogens, and 2 oxygens. All right? Now, why is this hydrogen not included with those hydrogens there? Well, it's again, as we mentioned earlier in problem where we were talking about acetic acid, problem 134. This is another representation of the acetic acid. This H is showing us, again, remember we had the 2 carbons bound to each other, 3 hydrogens coming off here, and we had our oxygen atoms coming off of here, and one of these oxygen atoms was connected to another hydrogen. And in acetic acid, an acid is a compound that when placed into water, a hydrogen comes off. And so this is written in a way, again, to remind us that this is an acid. There's that hydrogen ready to come off, and it's this one. That hydrogen is ready to come off. So this is acetic acid. All right? This is the acetate ion, and it's connected to an H plus ion there. All right, the last one, E on 140. NH4, 2 HPO4. In parentheses, 2 HPO4. HPO4. Okay? This is called the ammonium ion. Ammonium ion. And there are 2 of these ammonium ions. That's what the 2 on the outside of the parentheses means. HPO4. 1 hydrogen here, 1 phosphorus here, and 4 oxygens. This is called the hydrogen phosphate ion, polyatomic ion. All right? This is called ammonium hydrogen phosphate. Okay? So, how many nitrogens are there? Well, in these parentheses is NH4, and there's 2 of them, so there's 2 nitrogens. In this parentheses, there's 4 hydrogens, and there's 2 of those, so there's 8 hydrogens. But there's also this 9th hydrogen out here, so there's 9 hydrogens. Phosphoruses, there's just 1. No subscript here and no parentheses that we have to identify identifying more than 1 of these groups. So just 1 phosphorus. 1 phosphorus. How many oxygens? 4 oxygens. All right? And again, this compound is called ammonium hydrogen phosphate. All right, so 142 now. How many atoms of each kind are represented in the following formulas for each name the elements present? So basically the same thing. Alright, so the first compound, Ni for nickel, ClO4, ClO4, perchlorate ion, and there are 2 of the perchlorate ions. Alright? 2 of the perchlorate ions. And the perchlorate ion has a -1 charge, therefore the nickel has a +2 charge, and because the nickel has a +2, this is called nickel 2 perchlorate. Alright? Let's see. So in this we have 1 nickel, we have 2 chlorines, because there's 1 chlorine in this parentheses and there's 2 of these parentheses, and we have 8 oxygen, because there's 4 oxygen in here and there's 2 of them. 1 nickel, sorry, 2 chlorines, and then 8 oxygens. This compound here, carbon, COCl2. Alright, this is an organic compound, and there's 1 carbon, 1 oxygen, and 2 chlorines. The next one, K2Cr2O7, potassium dichromate, K2Cr2O7. Potassium, the chromate, or the dichromate ion, has a -2 charge. Potassium ion, 2 of them, have a +1 charge each. Therefore, we have, in this compound, we have one chromate for every 2 potassiums. So there's 2 potassiums, and we know that again by the 2 subscript, 2 chromiums, and there's 7 oxygen. All right, our next compound, the chemical formula for the next compound, CH3CO2H, CH3CO2H. All right, we see we have 1 carbon here, 1 carbon there, that's 2 carbons. We have 3 hydrogens here and 1 hydrogen there, that's 4 hydrogens. And we have 2 oxygens. All right, so that's the answer. And again, if you've been following along, we've been seeing this chemical 3 times now, and this 3rd time we have a different type of formula. Carbon with our 3 hydrogens, carbon connecting to 2 oxygens, and one of those oxygens has a hydrogen. Again, this is our acetic acid. Okay. All right. And the last one is the ammonium hydrogen phosphate again. So we just did that one, but we'll do it again. I don't know why they have it twice in here. NH4, and there's 2 of those. That's the ammonium ion, 2 ammoniums. Hydrogen phosphate, PO4. All right. Here again, how many nitrogens? 2 nitrogens. 4 hydrogens plus this one, so there's, or 4 times 2, 8, plus 1, so there's 9 hydrogens, 1 phosphorus, and 4 oxygens. All right, that leads us to 144, number 144. Number 144, how many atoms of each element are present in each of the following expressions? 3N2O. All right, now when there's coefficients in front, that means there's 3 of these things, 3 NO2s, or N2Os. So that means there's 6 nitrogens and 3 oxygens. All right, that's part A there. Number 144. B, 144B, CH3, 2S, CH3, 2, and then there's a sulfur. So this is a methyl group, dimethyl sulfide, all right? Di, meaning there's 2 methyls, so methyl, dimethyl sulfide. We don't need to know the naming system for these yet, but that helps us out a little bit. So we see that there's not just 1 of these though, as the problem indicates there's 4 of these. 4 of these CH3 2 S's. So in this compound we have, in one of these compounds, each one contains 1 sulfur, 2 of these CH3 groups, therefore 2 carbons, H3, 6 hydrogens. So if we want to multiply all that by 4, because we have 4 of them, so we have 4 sulfur, 8 carbons, and 6 times 4, 24 hydrogens. All right? So that's part B. Part C, the compound is 2 copper sulfate pentahydrates. So we have 2 CuSO4s, pentahydrates. Penta meaning 5. H2Os. Now this compound, do you remember what this compound's called? A compound where you have water molecules associated with it again? Do you remember what it's called, Filmer? It's called a hydrate. Hydrate. So this is copper sulfate pentahydrate, and we have 2 of these molecules. That 2 again refers to how many of these we have all together. So if we have 2 of these, then we have to double everything. So we have 1 copper here, 1 sulfur, 1, 2, 3, 4, plus 5 oxygen there. So we have 9 oxygen. But 9 times 2, right? So I'm not going to go all the way down. 9 oxygen, 1 copper, 1 sulfur, 9 oxygen, and then 10 hydrogens. But again, we have to multiply all that by 2 because there's 2 of those. So we have a total of 2 coppers, 2 sulfurs, 18 oxygen, and 20 hydrogen. Alright? Again, that 9 oxygen is because there's a 4 subscript on the oxygen. That subscript only refers to this because it's not on parentheses. It's just to that one atom. And we have 5. This 5 right here only refers to how many water molecules. So we have 5 additional oxygens plus these 4, so that's 9. And we have 2 of that many. Okay? 146. All right. So now we're on problem 146. It says write the chemical formulas for the following molecules and explain how samples containing them can be chosen to demonstrate the law of multiple proportions. All right. So in these little sketches down there that they have for us, we have 2 black atoms bound together. Those black ones are carbons. This carbon here has 2 hydrogens, 2 whites on it. It has a red on it, which is an oxygen, and coming off of that oxygen is another hydrogen. This has 2 hydrogen atoms coming off of it, and we have another hydrogen, or oxygen, and coming off of that is another hydrogen. All right. How many carbons altogether? How many black atoms? 2. There's 2 carbons. How many? That's our black atoms, right? How many hydrogens? 1, 2, 3, 4, 5, 6. 6 hydrogens. 6 hydrogens. Those are the white, or the white balls. And then we have 2 oxygens. All right. So write the chemical formulas for this one here. We could write C2, H6O2. All right. And then our other chemical formula, or other chemical there, we have a chemical like this. Whoops. Black bond to an oxygen. Alright, so this is carbon again. 2 more carbons off of the side of it. 1, 2, 3, 4, 5, 6 hydrogens all together. So we have 3 carbons here. So this part up here is for the top part. This is for the bottom part here. We have C3, H, 1, 2, 3, 4, 5, 6, and then 1 oxygen. Alright, so the question is, how does this refer to the law of multiple, how samples containing them can be chosen to demonstrate the law of multiple proportions? The law of multiple proportions, it means that if I put some carbon and some hydrogen and some oxygen into a container and react it at a given temperature, pressure, whatever, I'm going to get a specific compound, right? I'm going to get one kind of compound. But if I change the pressures and change the concentrations or conditions, the temperatures, etc., then when I do the reaction again, even with the same materials, I could get a different compound. That's the law of multiple proportions. That chemicals can combine in different ratios, different proportions, under different conditions. All right. In general, if you do one reaction the exact same way all the time, you'll always get the same types of chemicals being produced. But the law of multiple proportion was that people identified early on that it was possible to make different kinds of compounds even with the same chemicals. All right. So that's the law of multiple proportions. Number 148 here. All right? So it says consider the balanced equation, and it gives us a balanced equations. Iron nitrate, 2 iron nitrates, FeNO3 plus, I'm going to have to write that small. Okay. 2 FeNO3 plus 3 Na2CO3 yields Fe2CO3. There's 3 of those carbonates plus 6 NaNO3. That's sodium nitrates. So this is iron nitrate plus sodium carbonate yields iron carbonate and 6 sodium nitrates, right? So that's how you say this in English. It's written in chemistry, but you can say it in English. 2 iron nitrates, and this is iron 3 nitrate, so 2 iron 3 nitrates. The 3 refers to what the charge on this iron atom is. 2 iron 3 nitrates plus 3 sodium carbonates. Like this. 3 sodium carbonates yields 1 iron 3 carbonate and 6 sodium nitrates. All right? So there it is. It's the balanced equation. And question A is, how many atoms of sodium are on each side of the equation? On the left, we have 3 of these compounds, Na2CO3s. So if we have 3 of those, 3 Na2CO3s, then that means we have 2 sodiums for every one of these, and we have 3, so that's 6 sodiums on the left. Over here, we have 6 NaNO3s. 6 of these NaNO3s. That 6 again refers to how many NaNO3s. So the number is 6 as well. So the answer is A. How many atoms of sodium are on each side of the equation? 6. 6 on the left and 6 on the right. How many atoms of carbon are on each side of the equation? Now again, from the first sentence said, consider the balanced equation. If it's balanced, you know that the answer is going to be the same on both sides for all of these. So carbons, how many carbons are on the left and the right? Well, there's 1 carbon in the carbonate polyatomic ion here, the carbonate ion, and there's 3 of them, 3 of these all together. So there's 3 carbons, and so there should be 3 carbons on the right, and we can see that that's true. Here we have the carbonate ion, but we have 3, that subscript which is outside the parentheses, we have 3, and you can see it probably better in your book. So the answer is 3. How many oxygen atoms on each side? We have on this side, starting right here, NO3. So inside this parentheses, there's 3 oxygen atoms. But there's a 3 subscript for those parentheses. Therefore, that's 9 oxygen atoms in this little section here. But there's 2 of them, right? So 9 times 2. So we'll write this down. Do our accounting good. So that's 18 oxygens here. How many oxygens here? Well, there's 3 oxygens here, and there's supposed to be 3 of those. So that's 9 oxygens. So that's 27 oxygens altogether on the left. So there should be 27 oxygens on the right. Again, oxygen, 3 of them here. This is the iron 3 carbonate. And the oxygens, there's 3 of them, and there's 3 carbonates, so that's 9 altogether there. And then down here, O3, sodium nitrate, NO3. There's 3 oxygens, and there's 6 of those 3 oxygen components. So that's 18. So that's again 27. All right, so there's 27 oxygens on both sides. How many iron atoms are on both sides? Here we have an Fe, NO3, 3, 1 Fe, but there's 2 of these iron nitrates. So that's 2 irons on the left. On the right side over here, we should be 2 as well. We can double check. Fe2. So in that compound right there, we see that there's 2 irons as well. So those are the answers. That was 148. Here's 150. When sulfur impurities in fuels burn, they produce pollutants, sulfur, such as sulfur dioxide, a major contributor to acid rain. The following is a typical reaction. And then they show a hydrocarbon. This way? Down like that. They show a hydrocarbon. Now, a hydrocarbon, again, is a carbon and a hydrogen compound that contains carbon and hydrogen. And this is the sulfur with CH3, CH3, right? They show it like this, though. You have a carbon with a big yellow. This is yellow. Another carbon, and you have 3 oxygens coming off of it. Right? This is the compound that they show. And then they show a combustion reaction. A combustion reaction is where you combine something with oxygen. So it's plus oxygen, not just oxygen atoms, but oxygen gas, oxygen molecules, okay? So an oxygen molecule is 2 oxygen atoms. That's 1 oxygen molecule, okay? They combine together, and the products are, so these 2 combine together to yield, and this is all in your book, right? The yellow atom, and it has oxygens coming off of it now. And we have carbon dioxide, carbon with oxygen coming off of it. And the other product should be water, hydrogen with, or H2O, right? 2 hydrogens on 1 oxygen. All right? So this is a combustion reaction. Combustion reactions occur in cars all the time, right? We're combusting our fuel. We're burning our fuel. We're combining the fuel with oxygen to produce usually just carbon dioxide and water. But if your gasoline has impurities such as sulfur, that yellow molecule or that yellow atom, if it has sulfur, then you're going to get sulfur dioxide. And sulfur dioxide, like it says, is one of the principal components for acid rain. And we have this problem here in Hawaii too. We have one of the hugest factories in this side of the world constantly polluting the air. It's over on the Big Island. It's making sulfur dioxide almost 100 times more than any other factory. I'm not exactly sure how much more it is, but a lot more than any other factory in the northern or the western United States. But it's not really a factory, it's the volcano, right? The sulfur dioxide is constantly coming out of that volcano and causing acid rain. So that's one reason why there's a big chemical need for people to be sure that fuels are sulfur free. Now, sulfur dioxide here in the middle of the ocean, that's not too big of a deal, but sulfur dioxide in the inner cities, that can cause a lot of problems. If you breathe this acid rain, or sulfur dioxide, for example, it will combine with water to form sulfuric acid, sulfurous acid, other types of acids, and it will damage the tissue in your lungs. The same thing with nitrogen. If this sulfur wasn't yellow, if this wasn't a yellow molecule, perhaps it's a blue atom, which is a nitrogen atom. If it were a nitrogen atom combining with oxygen, the same products would occur. You would get nitrogen with oxygen, and those nitrogen with oxygen molecules will also combine with water and produce not sulfuric acid but nitric acid or nitrous acid, and those are also components of acid rain. So that's why when we're burning our fuel, we want to be sure that it's just carbon and hydrogen, no impurities like sulfur and nitrogen. All right? So on the left are the reactant molecules. This is what the problem says. On the left are the reactant molecules, and on the right are the product molecules in a chemical reaction. How many molecules of each kind are necessary to have a balanced chemical equation containing the smallest total number of molecules? Write the balanced chemical equation using the chemical formula. So we want to write the balanced equation for this process. Well, let's start off by writing what we know. We know that this is a sulfur, 2 carbons, so we could start carbon 2, S1, we can start with have the hydrogens next, C2, H3, S1. That's this compound right here. C2, 2 carbons, 6 hydrogens, 6 hydrogens. C2, 6 hydrogens, and then 1 sulfur. All right? And we combined it with oxygen gas. So I'll put a plus here, O2, 2 oxygens, right? We combined it with oxygen gas. All right? What are the products of this reaction? The products are SO2 and CO2 and H2O. All right, so is that okay? All right, so we have O2 combining with our dimethyl sulfide, and it yields sulfur dioxide, carbon dioxide, and water. Okay, so we want to balance this equation. Well, if we start on the left with our carbon, let's move this plus over to the left just a little bit. We start on the left with the carbon. We see we have 2 carbons, so we're going to need 2 carbon dioxides, 2 carbons on the right. So now there's 2 carbons on the left and 2 carbons on the right. We look at the hydrogen. We have 6 hydrogens on the left, and if we need 6 hydrogens on the right, we can add a 3 right here, and that'll give us 6 hydrogens on the right. Correct? We look at the sulfur. We have 1 sulfur on the left, 1 sulfur on the right. That's balanced already. So we're balancing this equation by making sure there's the same number of carbons, hydrogens, and sulfurs on both sides, and ultimately oxygen. Now oxygen, we can look at the right now. We see there's 2 oxygens on the right, but we see that we have 3 oxygens here, 4 oxygens there, 5, 6 oxygens there, all together, right? 1, 2, 3, no, 1, 2, 3, 4, that's 7, 8, 9. So we have 9 oxygens all together. Let's do that again. 3 of these, 3 here, 4 there, so it's 3 plus 4, 7, and then plus those 2, that's 9. All right? So we have 9 oxygens on the right, and we have 2 oxygens on the left. So what number can we put in front of this oxygen to make it so that we can have 9? Well, because it's O2, the oxygen molecules, we're going to have to put a fraction, like 4.5, right? And we can do that for a second, 4.5, but we know in a balanced equation that we don't want to have fractions. So to make this, so we see that 4.5 oxygens combines with 1 dimethyl sulfide to form 1 sulfur dioxide, 2 carbon dioxide, and 3 waters. That's that sentence translated into English, correct? But we don't want to have the 4.5 fraction in our final balanced equation. So we're going to multiply that by 2 to make it a whole number. Therefore, we're going to have to multiply this by 2. Therefore, we're going to have to multiply this by 2, this by 2, and this by 2. And we could go through it again. We have 4 carbons now. See 4 of them here. 4 carbons. 12 hydrogens, 2 sulfurs, 9 times 2, 18 oxygen, 6 oxygen here, 8 oxygen here. That's 10. No, 8, 9, 10. Let's see, 8 here plus 6 here. 6. So it's 14 hydrogens here, plus 4 more, 18. So 9 times 2 is 18, and we have 18 oxygens there. So the question is, it says write the balanced chemical equation. That's what we have here using the chemical formula. So we've done it. And we see that 9 oxygen molecules. Oxygen molecule again is this, 2 oxygen atoms together. That's how oxygen hangs out in the atmosphere. 9 oxygen molecules plus 2 dimethyl sulfides yields 2 sulfur dioxides, 4 carbon dioxides, and 6 water molecules. All right, so that was number 150. So, going on to number 152 now. All right, this is number 152. Is the following chemical equation for the combustion of octane, a component of gasoline, balanced? And their chemical equation says C8, H18, and we talked about that a little bit earlier, but that's octane. Oct referring to 8 carbons. Octanes plus 12 O2s, yielding 8 carbon dioxides and 9 waters. Alright, so is it balanced? If not, what is the smallest set of coefficients that would make the equation balanced? So basically, balance the equation and tell us what the balanced equation is. Let's translate this into English. It says 1 octane plus 12 oxygen molecules yields 8 carbon dioxides plus 9 waters. All right? So that is the English translation there. Let's just see if there's the equivalent number of elements of each atom on the same on both sides. How many carbons do we have on the left? We have 8. How many carbons do we have on the right? We have 8. So that looks good. How many hydrogens do we have on the left? What?
You're not in it, so you don't need to look at the camera.
How many hydrogens do we have on the left? 18. How many hydrogens do we have on the right? 18. All right, so that's good. How many oxygens do we have on the left? 24. How many oxygens do we have on the right? 8 times. So this is oxygen, there's 2 of them, but we have 8 of those carbon dioxides. That's a total of 16 oxygens here. And this is plus 9 oxygens there. So 16 plus 9, that's 25 oxygens. 25 oxygens. And on the left here we have 12 times 2, which is 24 oxygens. So everything's balanced except for the oxygen. And that's a pain in the neck, right? So we have to go back. And how would we approach this? What would be the best way to approach this? Well, at this point, it's not quite clear exactly what to do. So the best thing is to basically start over. All right? We start over. So we're back to octane, combining with oxygen to form carbon dioxide and water. And we want to know the ratios, the stoichiometry, the ratios. How many of these combine with how many of these to produce how many of these and how many of those. All right? Well, let's try to balance it. Carbon, 8. Carbon dioxide, we have to put an 8 here, right? To say that there's 8 carbons, 8 carbons. Hydrogen, 18. That means we need a 9 here. So we have 9 times 2, that's 18. But when we got to the oxygen part, we saw that we had over here, we counted that up earlier, that was 24. Oh, no, how many was it? 25 altogether. Let's see. 8 times 2 is 16 plus 9. So 16 plus 9 is 25. 25. Right. So how many oxygens do we need? Not 12, like it says in the book, but 12.5, right? Half of 25 is 12.5. Now that's not done either. It's balanced here, but a balanced equation shouldn't contain fractions if we can avoid it. So we have to multiply everything by 2 so that this 12.5 will be a whole number. 12.5 times 2 is 25. 8 times 2 is 16. 9 times 2 is 18. Oops. Yeah, that's right. All right. So now we have a balanced equation, and that's the answer to that problem. The question is, if it's not balanced, what is the smallest set of coefficients that would make the equation balanced? The coefficients are 2, 25, 16, and 18. So 2 octanes plus 25 oxygens plus yields 16 carbon dioxides and 18 waters. All right? So, and there you go. That's number 1.52. And that's the end of the problems for chapter 1.